With the recent advances in the artificial intelligence and machine learning field, we now have access to a wide range of technologies and techniques that enable computer systems to tackle a variety of data problems efficiently. Hey friends, my name is Saber and I'm a Ph.D. candidate and a machine learning scientist. In this video, I'm gonna give you an introduction to Autoencoder model and talk about its use cases. Whether you want to perform dimensionality reduction, denoise images to reconstruct the original image, or detect anomalies in time series problems, or even perform some fancy stuff like image segmentation, an autoencoder model can be a solution. Alright, an autoencoder is a type of artificial neural network that takes some kind of input data, and it can be images, vectors, audio, or whatever, and it first compresses the original input data into a lower dimension and then uses that lower dimensional representation of the data to recreate the original input. So why should we care about doing this? I mean, reconstructing the same input. In fact, we don't care about the output, but rather we care about the compressed lower dimensional representation of the data. By training the data to minimize the error between the original data and its reconstructed version, the model utilizes the neural network to find the most efficient representation of the input data, which contains the most important features, and those features will be summarized in the latent space. An autoencoder consists of three major components: the encoder, which is a module that compresses the input data into an encoded representation that is several times smaller than the input data; the bottleneck, which contains the compressed representations; and the decoder module that decompresses the bottleneck representation and tries to reconstruct the data back from its encoded form. But you might ask why we are setting the size of the bottleneck smaller than the rest of the layers. Well, this forces the information loss, and therefore the encoder and decoder needs to work together to find the most efficient compressed form of the input data. We need the latent feature vector space to be smaller than the encoder and decoder part, otherwise the resulting latent representation becomes useless as it simply copies the input to output. Now let's look back to a few applications of the autoencoders I mentioned at the beginning of the video and give you some examples. Anomaly detection is a perfect example where we train the model on normal instances so that if we feed it any outliers, they will be detected easily. In this case, we can use the reconstruction loss as a metric to detect outliers. Now, let's take a look at some fancy stuff. So far, I've talked about the concept of training autoencoders where the input and the output are identical, and the task is to reproduce the input as closely as possible. However, one way to develop a generalizable model is to slightly augment the input data, but still keep the original input as our target output. Imagine that you start with a normal MNIST digit and add noise to them and run that noisy image through the autoencoder model. The only difference is that instead of reconstructing the noisy image, you try and reconstruct the original image. By training our autoencoder model this way, we force the model to get rid of the noise, and eventually our model becomes really good at denoising images. This is how denoising autoencoders are used. Image segmentation is another example where autoencoders are used to take image inputs, preserving the spatial representation, and aim to output semantic segmented counterparts of the image. This technique is used in self-driving cars to segment different objects in their environment. Lastly, I'm gonna talk about neural inpainting approaches, where instead of adding noise to our input, you basically block parts of the image and force the AI model to reconstruct the missing parts. This approach simply powers many apps we use these days, including Magic Eraser, for example, on Pixel phones, which uses similar machine learning concepts. Alright friends, now that you got familiar with autoencoder models and learned about several applications of them, I'm gonna point you to this video which describes a project I'm working during my PhD studies. It exactly uses autoencoders to learn features of our DNA and RNA molecules and classify genes into different groups. If you're really into seeing autoencoders in action in a real life problem, make sure to check that out. Thanks for watching, and I'll catch you in the next video.